I derived, in the first place, a discretized version of the path integral, which I'll circle here, put in a box. It's represented as the limit as n goes to infinity. The path integral is an expression for the propagator, which we call k, which is otherwise the matrix elements in position space x of the unitary time evolution operator. You think of x0 as an initial position and x0 as a final position. This is over a time t that ranges from 0 to a final time just called t here. In other words, t is the elapsed time. The epsilon that appears in here can be thought of as a delta t. It's the fixed time interval divided by capital N, a parameter which is allowed to go to infinity, so that epsilon is a kind of a delta t which goes to 0. It's splitting up the time interval, finite time interval, into a large number of very small increments. And for each one of those, there's an insertion of a resolution of the identity, which is where these integrals come from. Last time we also explained how this integral can be interpreted, the path integral, this discretized version, can be interpreted as an integral over paths in configuration space. In the discretized version, these are discretized paths. But the exponent that appears here is apparently, or formally at least, it is a Riemann sum, an approximation to a Riemann integral. And we can write the integral in more compact form as a of x of tau. Tau here is a variable that just goes, it's a time-length variable that just goes between 0 and t. I'm using the symbol t here to stand for a fixed final time. So tau is a variable time that runs between the initial and final times like this. And the integral that appears here, formally, at least in the limit that n goes to infinity, it takes the form of a Riemann integral, which is the integral of the, denoted here as a of x of tau, but it is in fact the integral of the Lagrangian function over tau between the two time limits along the path x of tau, integral of LBT basically, or LB tau, in more abbreviated language. All right, so I think that takes us up to where we were. I'm really representing here two versions of the path integral, a discretized version where there's an explicit limit, and a more compact version, which is easier to remember and to write down. The d of x of tau, which appears here, is just notation for the quote-unquote volume integral in path space. It really represents the products of these dx's. We don't have any integrals over x0 or xn, of course, the initial and final x's, because those are fixed parameters of the path integral, the x0 is simultaneous x of n. And they're not variables of integration. That's a way of saying the path has fixed endpoints at the given two n times, 0 and t. But in between those fixed endpoints in n times, it's allowed to take on any position at all. All right. Now, the fact that the exponent of the path integral is appearing as an integral of the Lagrangian over time, something here I'm calling action functional, is striking because the action functional plays a prominent role in classical mechanics, in particular in the Lagrangian formulation of classical mechanics, and also Hamilton's principle. I assume that you've seen some of this in your undergraduate course in classical mechanics, at least in sketchy form. I don't think they usually go into it very carefully. So I'm going to say a few more words about it, go into a little more detail than you've probably seen before, in order to ultimately connect that with the path integral we see here. So what I'd like to do in the next few minutes is to sort of put the path integral on hold and just to review some aspects of the Lagrangian formulation of classical mechanics, the action functional, and the role that it plays in that. So here I talk about now quantum mechanics, and we'll go to classical mechanics. So the story in classical mechanics begins by speaking of a space of paths, which I can sketch again in the space-time diagram like I did yesterday for the paths in the path integral. Let's make it x and t like this. We'll choose two times, call them t0 and t1, an initial and final time, and two positions, x0 and x1. This is just one-dimensional problem, by the way, just for simplicity. We're working 1D. And by drawing lines here for the initial and final positions and the initial and final times, we get a rectangle in the space-time plane. The lower left corner is the x0, t0, which we think of as initial position and initial time. And the upper right corner is the x1, t1, which is a final position in time. Now, when we define a path as a function x of t, that passes through these initial positions, these given endpoints and end times. So it satisfies the condition that x evaluated at t0 is equal to x0, and x evaluated at t1 is equal to x1. If you sketch it on the diagram here, a path is a curve that goes through here like this. I'll call this x of t. It's a curve that passes from the initial to the final positions of times, which are just fixed. These are just fixed parameters of the problem, these four numbers, x0, t0, x1, and t1. Now, so this is what we mean by a path here. Even though this is classical mechanics, there's no requirement that this path satisfy the classical equations of motion, Newton's laws, F equals ma. It can be any path, although we will require it to be continuous, because you're usually continuous and actually smooth, because that's what you usually want in classical mechanics. All right. So this includes lots of crazy paths that have nothing whatsoever to do with the classical motion. They may go off in the wrong direction. They may linger at some point for a long time and then zing over to the final condition to get there at the right amount of time. There's all kinds of crazy paths that are in there. Now, for each one of these paths, we define a functional. We define a number. It's called the action functional. And it's defined as an integral from t0 to t1 of the Lagrangian function evaluated on the path, x of t, x dot of t, dt. It's an integral over time of the path, of the Lagrangian taken along the path. The Lagrangian is an ordinary function of x and x dot. It may also depend on time, but for simplicity, let's just say x and x dot here like this. And in the problems we're interested in, this is m over 2x dot squared minus v of x. We're just talking about simple one-dimensional kinetic energy, potential energy problems. It's kinetic minus potential energy. So that's the Lagrangian that we'll use. Anyway, this A is called the action functional. And it's defined on all paths, whether or not they're physical from a classical standpoint. Action functional. All right. Now, there is, however, something that characterizes the physical paths. As to say, x of t is physical. This is called, let me write this up. Right? This is called Hamilton's principle. So I'll write that out. Hamilton's principle, which was enunciated at least 100 years before quantum mechanics, says that x of t is physical. That means it satisfies Newton's laws, if and only if the functional derivative of the action with respect to the path x of t is equal to 0. Now, you may not have seen functional derivatives before, but I'm assuming you've seen at least a sketchy aspect of Hamilton's principle in your classical mechanics course. So let me elaborate on what this means and show you how this works out. So let's take a path x of t, which need not be a physical path, and let's consider another path which is nearby. So I'll sketch it here. It's supposed to go through the same endpoints at n times as the original path. So let's call it x of t plus delta x of t, for a nearby path. It's important to understand this notation delta x of t. Delta x of t is merely the difference between two paths that satisfy the endpoints of n-time conditions. The delta is not an operator. Delta of x is a function of time. However, the delta is a reminder that it's supposed to be small because we're talking about two paths that are nearby one another. So this function delta x of t has to satisfy the condition that delta x of t0 and delta x of t1 must be equal to 0, because otherwise the modified path wouldn't pass through the given endpoints and end times. But just a condition we impose on this. Now, let's take this action and let's evaluate it instead of on the original path. Let's evaluate it in the modified path, like this. So what do we get? Well, the action function along the original path, let me write this out. This is the same thing as integral from t0 to t1. The mass over 2 times x dot of t quantity squared minus the potential evaluated at x of t. And that whole thing integrated over time. This is just what we mean by integrating the whole dt to Lagrangian. We just take our path x of t, we differentiate it, get an x dot, plug it into this formula, we integrate it as a function of time. We do the integral, the number comes out, and that's what we call the action along the path. And remember that it does not have to be a physical path. All right, now let's evaluate the action of the modified path. This is the integral from t0 to t1. And then we've got the mass over 2. And then we've got x dot plus delta x dot, 1 squared. Then we've got minus the potential evaluated at x plus delta x. Those are both functions of time. And then the whole thing is integrated over time, gt. All right, action along the modified path. Now, allow me to expand out the right-hand side, assuming that delta x is small. So what this becomes is, let's write this. So this becomes, so we can expand this out. You see, this quadratic term expands into x dot squared plus twice x dot plus delta x dot squared. And the v here expands into v of x plus v prime of x times delta x plus 1/2 v double prime of x, a bit over on that room here, times delta x squared, and make that a double prime, plus a higher order term. So we can expand out the integrand in powers of delta x. And then let's collect the terms by orders in delta x. And let's call the terms t0 plus t1 plus t2 plus dot dot dot, where t just stands for term. That's the mnemonic here. But it's the terms that occur at different orders in the powers of the delta x, which is like a perturbation around the original path. And so it's pretty easy to collect formulas together for what these various terms look like. If we get to t0, what is that? That's just ignoring the delta x altogether. So that's the integral from t0 to t1 of m over 2 x dot squared minus v of x, integral integrated dt. And that, of course, is the original action along the original path, which is a of x of t. As far as t1 is concerned, it's the integral from t0 to t1. And now I'll collect the first order terms. There's the 2x dot delta x dot times m over 2, so I get a mass times delta x times x dot times delta x dot. And then for the potential energy, I get a minus v prime of x times delta x, and that whole thing is integrated dt. And then t2, the second order term, is the integral from t0 to t1. So now I need to take the quadratic terms, delta x squared here, delta x dot squared there, delta x squared there. So it becomes m over 2 delta x dot quantity squared minus v double prime of x times delta x squared dt, etc. You can keep on going. There's higher order terms as well. But for the second order, this is what we get. Now, remember the context of this is we're thinking of x of t as being a given path, so it's a definite function of time. We just pick somehow to draw a path. And delta x is a small variation around it. So the x that appears here is the original path, and by plugging it in here, these things, v of x, v prime of x, v double prime of x, and so on, just become functions of time, which are going to get integrated. All right. Anyway, those are the terms. Now, all I've done is take the action along an arbitrary, usually non-physical path, and just expanded it out to first order and the second order in the variations around the path. Now let's take a look at the T1, which is the first order correction, right here. Look in particular at the term x dot delta x. What I want to do is integrate this by parts. So that means I'll integrate the delta x, and then I'll differentiate the x dot and change the sign, and there's a boundary term. And so if you do this, then T1 becomes equal to the mass times x dot times delta x, evaluated at t1 to t0, plus the remaining integral, which is from t0 to t1. And then I have to change the sign, and so it's going to be minus the mass times x double dot times delta x. And then for the potential energy term, it's the same. It's minus v prime of x times delta x, and this is integrated dt. All right? Now, however, the delta x vanishes at the endpoints. That's so the modified path has the same endpoint and in-time conditions as the original path. And so this first term goes to 0 because the delta x here is 0 at both the upper and lower limits. As far as the second term is concerned, there's a common factor of delta x, which I'll take out. And so this turns into an integral from t0 to t1 of m times x double dot minus v prime of x multiplied times delta x, which is a function of time, of course, times dt. And now you can see an example of Hamilton's principle, because you see that this first order term vanishes if the original path is a physical path. The original path is a physical path if it satisfies Newton's laws. Newton's law says that the mass times the acceleration, this should have been a minus sign here, says the mass times the acceleration is the force, which is minus v prime of the potential, according to Newton. And so if the original path we started with was a physical path, then this t1 term vanishes. Conversely, if this t1 term vanishes for all possible choices of delta x, in other words, if we have a path such that when you make variations around the path, the action suffers no change at first order, then that path is physical, because if this integral vanishes for all choices of delta x, then the integrand has to vanish, and that implies Newton's laws. And that's what Hamilton's principle is. And this notation here is just a notation for what I just said in words. In fact, this quantity here actually is the functional derivative delta A of x with respect to x of t. It's just a definition of the functional derivative. It's that thing. So Hamilton's principle is equivalent to Newton's laws. All right. This is how this functional derivative works out. In the case of this kinetic minus potential Lagrangian. If you do it for a general Lagrangian, this is the same thing as minus ddt of partial of L with respect to x dot plus partial of L with respect to x. And that gets set to 0. Here should be the famous one of the Lagrange equations for the classical equations of motion. Yes?
Quick question. So in the when you are evaluating t1, what was the reason that the first boundary term vanished?
Here?
Yes.
Because we have two paths. We're starting with one path, x of t, in our path space. Passes through the given endpoints and end times, which are just parameters of this problem. x0, t0, x1, and t1. Those are fixed. Now, we want to take a nearby path, but it's supposed to be satisfy the same boundary conditions. It's just the rules of the game. We're only going to look at paths that satisfy the given boundary conditions in position and time.
Right.
And if that's true, since x of t satisfies the boundary conditions, the delta x has to go to 0 at the boundary, boundaries. That's the reason for this here. That's what leads to the vanishing of this boundary term here. Okay? Right. Now, so this is an illustration of what's meant by Hamilton's principle. So one way of saying this in more pictorial language is to say that the classical paths are characterized by the fact that if you make first-order variations in the path around the classically allowed path, the action suffers only second-order variations. That is to say, t1 is 0, and t2 may be non-zero. That's the second variation of the action, but the t1 term vanishes. And this is equivalent to the functional derivative there. Delta A, delta x of t equals 0. This Hamilton's principle is stated in many books by saying that the action is minimum along the classical motion. And in fact, Sakurai repeats this. It's actually not really correct, because a more proper way of saying it is to say the action is stationary on the classical path. All we've done is shown that the first order variations vanish around the classical path. It's like just because the derivative of a function equals 0 doesn't mean you're a minimum. You could be a maximum, or you could be in many dimensions of the saddle point. There's all kinds of possibilities. Yes?
Is it possible for there to be several extrema of the...
Absolutely. In fact, there might not be any. This is another error which is made in many books. They say there's a unique classical path connecting these endpoints and end times. In general, there's not. There may be many of them.
So how do you know which one actually happens?
Well, they all happen, and every one of them that happens satisfies this condition. It's for all of them, it's true that it's like finding if you have a function, you may have many extrema here and here and here, And for each one of them, the first derivative vanishes. Likewise, in path space, this is really like a derivative, first derivative in path space. You may find there's more than one path. To give you an example, let's take a particle in a box with hard walls. If I start off at this wall here at some time, let's say t equals 0, and I want to get back to the same wall at the final time t, so the initial x and final x are the same. Well, one way to do it is just have zero velocity and just stay there. And you certainly get back to that final position. Another way to do it is give yourself enough velocity so that in time t you go over and hit the wall and bounce and come back. That's another classically allowed path. Double the initial velocity and you go 4 times and come back. In this case, you see there's an infinite number of classical orbits that satisfy the given initial conditions and initial and final conditions and initial and final times.
So then to differentiate, you have to know something about the initial conditions to know like which.
No, you see, it's interesting because the functional derivative leads to a differential equation. So the usual thing you do in classical mechanics is solve the differential equation with respect to given initial position and velocity. But here, this is the original formulation is in terms of an initial position and a final position, which is kind of a boundary value problem in classical mechanics. All right. As I say, this is not really a principle of least action, it's a principle of stationary action. However, it's interesting to ask whether or not the action really is a minimum along the classical path. It's just an academic question at this point. But if you wanted to answer that, you need to go on to the second correction term, the T2. So let's take a look at T2. Because it turns out that although this is an academic question in classical mechanics, it actually has an effect in quantum mechanics. So let's look at the second variation, T2. And once again, I'd like to take the first term and integrate by parts, right? This is delta x dot times delta x dot. You'll allow me to use my fingers here, delta x dot, delta x dot. So we'll integrate one of them giving delta x, differentiate the other one gives delta x double dot, and there's a boundary term. So this becomes m over 2 times delta x double dot times delta x evaluated between the limits t1 and t0, plus an integral from t0 to t1. And now what we've got with a change of sign is minus m over 2 delta x double dot times delta x. And then for the potential energy term, I just copy it down. This should have been 1/2 here. See the 1/2 up there. It's just a Taylor expansion. So it's minus 1/2 v delta prime of x, delta x squared. That's T2. And once again, you'll see this first term, boundary term, goes to 0 because of the boundary conditions on delta x, and we're left with this integral. I just remembered something I wanted to say a moment ago before I got launched into T2. So let me put T2 on hold and then go back up to the previous board. Because I want to say something, which is that the T0 is the action along the unperturbed path. And as I just explained, if the path is physical, then T1 is equal to 0. You can evaluate the action along any path, whether it's physical or not. However, if the path is a physical path, a classically allowed path solution of Newton's laws, then this just gives us a number, which is the action evaluated on that classical path. And there's a question about whether that number, that action on the classical path, has any particular meaning in classical mechanics. This is a question that Hamilton asked himself in the 1840s, I think it was, and it turns out that it does have an interesting physical role in classical mechanics. Let's make the following definition. Let's take the action and evaluate it along, I'll call it x of CL of t, meaning a classical path or a solution of Newton's laws. Well, if it's a classical path, then it has to satisfy these boundary conditions, x0, t0, and x1 and t1. And so it's a rather special kind of a path. And the number that comes out, therefore, we'll give it another symbol, is a function of the x0, x1, t0, let's put it this way, x0, t0, x1, and t1. This is defined to be the action evaluated in the classical path. This is not a functional, it's an ordinary function of these 4 parameters. Now, in fact, in view of the question that was just asked about whether the classical path is unique or maybe more than one, And if so, you can evaluate this along different paths. If you want to introduce, let's say, a branch index, B equals 1, 2, or so on, labels the classical solutions. Classical solutions, then this S depends on the B. And when I say classical path here, I should put a B index on it to indicate which classical path we're talking about. But anyway, there's this function that's created in this way, and this function is called Hamilton's principal function. Now, Hamilton's principal function is a function of these four parameters. Now, one of the things that Hamilton showed was that this function satisfies interesting differential equations. In particular, ds with respect to x1 is equal to the momentum at the endpoint of the path. And ds with respect to x0 is equal to minus the momentum at the beginning of the path. Likewise, ds dt1 is equal to, with a minus sign, the Hamiltonian at the end of the path, the energy at the end of the path. And ds dt0 with a plus sign is equal to the Hamiltonian at the beginning of the path. I won't prove these in class here, although I did prove them in this appendix that I wrote on classical mechanics. So if you want to see how these are derived, you can look in there. Anyway, this is Hamilton's principal function. That's the action evaluated along the classical path. Now, to go back to the T2, let's suppose we've got a classical path. That's what I'm really thinking about. Here we're evaluating this action on a classical path and considering variations. And the first variation, T1, is 0, in accordance with Hamilton's principle. But we're going to look at T2 because we want to find out whether the action is really minimum or not. So here's T2 by integration by parts. I've re-expressed it in terms of this integral. Now, here's some convenient notation. Let's let f of t, g of t, etc. be functions, just ordinary functions. In fact, let's make them real functions, defined on the interval from t0 to t less than or equal to t1. It's the time interval of this classical problem. And let's define a scalar product, which I'll use Dirac notation for, of these functions, to be equal to the integral from t0 to t1 of f of t times g of t dt. It looks just like the scalar product of wave functions in quantum mechanics, except I didn't put a star in the f, and the only reason I didn't do that is that these are real functions. Another difference, of course, is the integrals over time instead of over space, and this is a classical problem here, but it formally looks like a scalar product in quantum mechanics. In fact, it defines an Edwards space of function of time. Now then, allow me to take this integral here and rewrite it in a slightly different form, t0 to t1, and then let me put the delta x of t on one side, like this. And then in the middle, I'll put minus m over 2 d squared dt squared, then minus 1/2 v double prime of x of t. This is the classical path here, the x of t. And then I'll put a delta x of t on the other side, and then we integrate this over time dt. It's just a rewriting of this integral. Let me call this thing in the square brackets here. Let me call this v. It's an operator. It's an operator that acts on functions of time defined on this interval. And with that notation, we can see that we can write this as delta x sandwiched around v. It looks like an expectation value of an operator in quantum mechanics. So now, if we want to know whether the action is minimum along the classical path, the first variations vanish. What we need to show is that the second variations would be positive for all choices of delta x, all non-zero choices. If delta x was 0, of course, the variation t2 would be 0. But in order for that to be a minimum, it would mean that if you make any variation along the classical path, the action will only increase. That would be the condition for a minimum. But that, in turn, is equivalent to saying that this operator is positive definite. So if you want to find out if the action is really a minimum, you take this operator and you find its eigenvalues, And if they're all positive, then the action really was a minimum, and what the books say about least action is actually correct. The question is this a positive definite operator? The answer is, it depends on the potential, and it also depends on the time interval. Sometimes it is, and sometimes it isn't. So, in general, this Hamilton's principle is not a principle of least action, it's a principle of stationary action. In any case, this is what you need to do if you wanted to find out, is examine the eigenvalues of B. All right. Now, I think that's all I want to say about Hamilton's principle in classical mechanics. It's a good deal more than you probably saw in your classical mechanics course. And allow me now to go back to the path integral here. So where we stand at this point is we notice that the exponent is formally similar to the action interval that appears in classical mechanics. The path x of t satisfies the same type of boundary conditions that it passes through given positions at given endpoints and given end times, as in the classical problem. The path itself is rather different. It may be these Brownian motion or white noise type paths that I described last time, so they're particularly not smooth. But except for that, it's very similar. And so the suggestion is raised is that the path integral provides some kind of a connection between Hamilton's principle in classical mechanics and the quantum mechanics of the propagator. By the way, Hamilton's principle was noticed 100 years before quantum mechanics. In fact, this functional derivative vanishing of the functional derivative is equivalent to Newton's law, is known. But no one knew why it was true. The real explanation of Hamilton's principle only came with finding this path integral in the 1940s, early 1950s. All right. So, in any case, here's the idea: is that in the limit in which h bar is 0, the quantum problem should go over to the classical problem. We should see classical mechanics emerging. However, if h bar goes to 0, it means that this exponent here gets to be large, or more exactly, it becomes rapidly oscillating as the path varies. And so what happens is that what this means is it becomes rapidly varying. H bar is close to 0. It means that typical paths in path space interfere destructively with their neighbors which are nearby because of the rapid oscillations. The exception to that, however, is paths in path space for which the action is stationary, because then nearby paths in path space are nearly in phase with the given path. Well, by Hamilton's principle, those are the classical paths. So the classical paths make their privileged appearance known by the fact that they are in path space in phase with their neighbors. And the result is that this integral should be dominated. Integral over all path space, including a lot of crazy paths like white noise, but the integral should be dominated by regions of path space that lie around the classical paths. And that is, in fact, how the classical mechanics emerges from the path integral. Now what I want to do is to go into this in more detail and show you how this comes about in more explicitly. So this idea that if you have an integral with a rapidly oscillating exponent, that the main contributions come from the places where the phase is stationary. This is called the principle of stationary phase, something of that sort. And it's an approximation that's frequently used for approximating integrals. So let me switch over now to just pure mathematics and give you some background on what's called the stationary phase approximation. Let's take a one-dimensional integral over a variable x. And let's say there's a phase, it's e to the I phi of x like this. And I'll divide by a quantity kappa, and what we want to think about is kappa going to 0, so kappa is a small number. Well, as kappa goes to 0, the integrand, which is e to the I phi of x over kappa, oscillates more and more rapidly. So the amplitude is, of course, equal to 1. We're thinking of phi here being a real function. So if you think about this on the integrand and on the x-axis like this, it looks something like this for some value of kappa. And if I take, it's supposed to be kappa. And so if I take kappa over 2 divided by 2, you get the same amplitude, but you have oscillations that are twice as, have only 1/2 the wavelength, twice as fast, like this. When you get these kind of rapid oscillations, what happens is the area of the one positive lobe nearly cancels the area of the subsequent negative lobe. And so you get alternating signs of nearly canceling numbers. And the result is that this integral goes to 0, as kappa goes to 0. It just oscillates itself to death. Another question is, how does it go to 0? When kappa goes to 0, how does the answer depend on kappa when kappa is small? And the answer to that question depends on whether or not the function phi has any what we call critical points or stationary phase points. So here's what I'll call a critical point. A critical point is mathematical terminology. Let's call it x bar. X bar is the root of the equation phi prime of x bar equals 0. In other words, x bar is just a place where the derivative of the phase is equal to 0. Math folks call it critical points. I'm going to call it a stationary phase point because it's more pictorial for our applications. It's a point of the variable x, which is the variable of integration here, at which the phase is locally stationary. Its first derivative vanishes. Or another way to say it is that the phase, at a stationary phase point, first-order variations in x around x bar produce only second-order variations in the phase. This should remind you of Hamilton's principle in that space. And the reason for that is that at stationary phase point, it means that the integrand is in phase over a larger range of the variable x than it is at an ordinary point. Instead of getting oscillations like this, what you find is there's one central lobe around x bar, which is in fact not cancelled by its neighbors. And it has a width which is the order of the square root of kappa. And so it contributes a total integral, which is the order of the square root of kappa. So the answer to this question up here is this, as it turns out, goes as the square root of kappa if there exists stationary phase points. And if there are no stationary phase points, this goes to 0 faster than any power of kappa. It's exponentially fast. It makes a big difference whether there's stationary phase points. So the approximation itself is straightforward. Let's just suppose that there is a critical point or stationary phase point x bar, and we'll just take phi of x and we'll approximate it in the neighborhood of x bar by phi of x bar. Let me let y is equal to x minus x bar, so it's the deviation away from the stationary phase point. And then doing a Taylor series expansion, we have y times phi prime of x bar plus 1/2 y squared times phi double prime of x bar plus etc. like this. Except the first term goes away because x bar is a stationary phase point. The first derivative vanishes there. And if I call this integral I here, let's call it equal to I, then I should be approximately equal to the integral over dx of e to the I over kappa times this expansion, phi of x bar plus I over 2 kappa phi double prime of x bar times y squared. And the dx, by the way, is equal to dy. It's just a change of variables. And so you can see the first term is just a constant phase. It's independent of the variable of integration, which you can take out. Second term I can write as another phase here. And as far as doing the second term, it's a Gaussian integral, which you can do. And so what you get is that the integral I is approximately equal to, first there's the constant phase, and I'll write up over here to the right, e to the I over kappa times phi evaluated at the stationary phase point. And then for the Gaussian integral, if you do that, you'll find the answer is this. It's square root of 2 pi I kappa divided by phi double prime of x bar. All right, this is called the stationary phase approximation to the original integral. Now, there's two things I need to fix up about this answer. The first one is that it involves the square root of I. And there's two square roots to anything, and you need to say which one you mean. If you do it right, the square root of I is considered to be e to the I pi over 4. However, if phi double prime, the second derivative, is negative, then in effect you can transfer the sign of the phi double prime over to the I, and then you get the square root of minus I, which is e to the minus I pi over 4. So you either get a plus or minus I pi over 4 for the phase, depending on the sign of phi double prime. Let's do this. Let's let nu equal the sign of phi double prime at the stationary phase point, and then rewrite this way, is to say I is equal to e to the I nu pi over 4, the square root of 2 pi kappa divided by the absolute value of phi double prime evaluated at the stationary phase point times e to the I over kappa phi evaluated at the stationary phase point. And this is a better version of the answer because it's clear about the phases. And now there's finally one more cosmetic change, not so cosmetic, I need to make to this, which again, as was pointed out, is that there may be more than one root of this. There may be more than one stationary phase point. Let's label the roots by a branch index. Let's call it d is equal to 1, 2, 3, and so on. Typically, there's a discrete set of roots. And if we do this, then the answer has to be summed over the branches, like this. Sum over the branches. The x bars depend on the branches, and nu depends on the branches because it depends on the sign of phi double prime, so put a branch index on that. And having made those changes, this now is the stationary phase approximation for one-dimensional integrals with rapidly oscillating exponents. It's really doing a Gaussian approximation to the integral around the stationary phase point. Now, let's do a generalization of this. Let's do the n-dimensional generalization. And I'm also just quoting answers in this case. Let's let x now stand for x1 up to x to n. And let's let x bar, which is the same thing as x bar 1 up to x bar n, be the stationary phase point, which is to say that it's a root of the equation that the derivative of the phase with respect to xi evaluated at x bar equals 0, and this is for all I going from 1 up to n. And by the way, the integral that we're interested in here, let me call it I, is an integral over n-dimensional space dnx of e to the I phi of the multidimensional x divided by kappa. The obvious multidimensional generalization of this. Okay. In other words, the stationary phase point is just a place where the gradient of the phase, multidimensional gradient of the phase, vanishes. And now we do the same thing. We take this phi and expand it out to second order. The first order terms will vanish at the stationary phase point because that's the definition of the stationary phase point. So we get a constant term and a quadratic term. The quadratic term is a multidimensional Gaussian integral. It involves a symmetric matrix, which is the second derivative of phi. That can be diagonalized and converted into a bunch of one-dimensional integrals that look just like that. So the details of this are contained in the notes. I'm just going to quote the answer for you. The I then turns into this. It is an e to the I nu pi over 4. And you get the square root of 2 pi kappa to the nth power divided by the denominator, the absolute value of the determinant of the second derivative of phi with respect to xi and xj, evaluated at the stationary phase point. Then multiply it times e to the I over kappa times phi, evaluated at the stationary phase point. Now, this is not quite done yet because I need to say what nu is. In the one-dimensional case, nu is the sign of the second derivative. In the multi-dimensional case, you need to look at the eigenvalues of the second derivative matrix. Some of them may be positive and some negative. If they're positive, they give you a plus pi over 4, and if they're negative, they give you a minus pi over 4. So the nu here is defined to be, let's call it nu plus minus nu minus, where nu plus and minus are equal to the number of positive or negative eigenvalues of the second derivative of the phase, xi, xj, evaluated at the stationary phase point. It's a symmetric matrix here. So this just accounts for the plus or minus pi over 4 phase factors that come from the n different Gaussians. The determinant is the product of the eigenvalues. It's really the product of these phi double prime factors for each of the dimensions that we diagonalize phi. And then finally, one final change is that in case there are multiple roots, we need to put in the sum of the branches. And again, it's the x bar is labeled by the branches, so it appears there and there. And it also appears in the nu, because the nu is related to the value of x bar. And this final box down here is the multidimensional version of the stationary phase approximation. All right. Now then, so the suggestion is that we carry out I'm sorry to have to cover that up, but I'll pull this down in a minute so you can see that again. But let me go back to the path interval and say what we're going to do next. Is we're going to apply the multidimensional version of the stationary phase approximation to the path interval. The idea is that what I call kappa up there is going to be replaced by h bar, which we'll think of as being small, leading to a rapidly oscillating exponent, in which the value of the exponent is the classical action, the action function along the path. And what we'll do is we'll find the stationary paths, which are like the stationary phase points. Those are the classical paths. And we'll carry this out, we'll carry the expansion out to second order, because that's what you need to do to get these Gaussian integrals in stationary phase approximation. This will mean we'll be considering paths in path space that not only include the classical paths, but also include variations around the classical path, like a little tube in path space around the classical path. And then by expanding the action out to second order, we then in effect have a Gaussian integral, multidimensional Gaussian integral, which is doable. And it gives us an approximation, actually a semi-classical approximation to the propagator, which is built around the structure of the classical paths connecting the initial and final positions in a given amount of time. Okay. So there's a fair amount of algebra in doing this, but I want to be clear before I get into that what the general strategy is. All right. In fact, I'm not going to go through all the details of this in lecture. Most of them are in the notes, and you can read about them there. But I want to really, I think the essential ideas here are more important than all the details. All right. So I'm going to take a mental picture of this discretized version of the path integral. As you see, it's an capital N minus 1 dimensional integral where we're going to let n go to infinity. The phase, if I identified the h bar here with the kappa that I was using before, the phase is the everything in here except the I over h bar, so it's epsilon times that sum. So the epsilon times the sum is an approximation of the action integral, classical action integral. All right. So, and now you see why I went to second order in the expansion of the classical action function, because these second order terms are going to give us the Gaussian integration in the stationary phase approximation. And this, by the way, is why it makes a difference in quantum mechanics whether the classical orbit minimizes the action or not, because this is going to affect the phase of the propagator. Probably the most amazing thing about all of this is the fact that the path integral gives an explanation for Hamilton's principle. All right. So, although I covered this up, I'll have to cut down and have to very well my notes. So, using this notation, so let's take the kappa, which is up here, and let's replace it by the h bar. And then what I call phi of the x's, this is going to be an x1 up to xn minus 1. That's equal to everything in our discretized exponent except for the I and the h bar. So let me write this out. This is epsilon times the sum of j equals 0 to n minus 1. And then we have m over 2 times xj plus 1 minus xj squared over epsilon squared. This is a discretized kinetic energy, delta x over delta t quantity squared times m over 2 minus potential energy v evaluated at xj, like this. So the first thing we're going to need is to find the critical points. So to do that, we can differentiate this with respect to, let's say, xi. And if you do this, what you find is, maybe I'll call it k because it might be more clear. Make it differential with respect to xk. What you find is this is epsilon times, and then you get this. You get the mass m, you get x minus xk plus 1 plus twice xk minus xk minus 1 divided by epsilon squared. That's from doing the differentiation here. And then you get minus b prime of xk, like that. Okay? That's what you get. And to find the critical or stationary phase point, we have to set this equal to 0. Well, setting this equal to 0 just means the thing in the square bracket is equal to 0. Let me just rewrite this in a slightly different form. The mass, I'll bring this term over to one side and keep that on the other side. It's xk plus 1 minus twice xk plus xk minus 1 divided by epsilon squared is equal to minus b prime of xk. Well, the epsilon is interpreted as a delta t. And what's in the numerator here is a discretized version of the second derivative of x. So what you've got here is a discretized version of the mass times the acceleration. And on the right-hand side, you've got the force evaluated at xk. So to solve the discretized version of the differential equation is what people do on computers when they solve them approximately. However, we're really interested in the limit that n goes to infinity. So in the limit that n goes to infinity, if I take n goes to infinity, this turns into a continuous differential equation, which is m times dx squared of tau, let's say, d squared x of tau squared is equal to minus the potential b prime evaluated at x of tau. And this just repeats what we knew we had defined, is that these stationary phase points, this is Hamilton's principle, stationary phase points of the action functional are precisely the classical ordinates. For a discretized version of the path integral, they're appearing in discretized form, taking the limit to give us the continuous classical task. So the x of tau that satisfy this are the classical tasks.
Just as a time jacket.
What's that?
Time jacket.
Oh, okay. All right. Well, that's all then. This is, so we'll take up with this next time and finish this stationary phase. The integral of the Lagrangian function over tau between the two time limits along the path x of tau. Integral of LDT, basically, or LD tau, in more abbreviated language. All right. So I think that takes us up to where we were. I'm really representing here two versions of the path integral, a discretized version where there's an explicit limit, and a more compact version, which is easier to remember and to write down. The d of x of tau, which appears here, is just notation for the quote-unquote volume integral in path space. It really represents the products of these dx's. We don't have any integrals over x0 or xn, of course, the initial and final x's, because those are fixed parameters of the path integral, the x here, the same thing as x of n. They're not variables of integration. That's a way of saying the path has fixed endpoints at the given two n times, 0 and t. But in between those fixed endpoints and n times, it's allowed to take on any position at all. All right. Now, the fact that the exponent of the path integral is appearing as an integral of the Lagrangian over time, something here I'm calling action functional, is striking because the action functional plays a prominent role in classical mechanics, in particular in the Lagrangian formulation of classical mechanics, and also Hamilton's principle. I assume that you've seen some of this in your undergraduate course in classical mechanics, at least in sketchy form. I don't think they usually go into it very carefully. So I'm going to say a few more words about it, go into a little more detail than you've probably seen before, in order to ultimately connect that with the path integral we see here. So what I'd like to do in the next few minutes is to sort of put the path integral on hold and just to review some aspects of the Lagrangian formulation of classical mechanics, the action functional, and the role that it plays in that. So here I talk about now quantum mechanics, and we'll go to classical mechanics. So the story in classical mechanics begins by speaking of a space of paths, which I can sketch again in the space-time diagram like I did yesterday for the paths in the path integral. Let's make it x and t like this. We'll choose two times, call them t0 and t1, an initial and final time, and two positions, x0 and x1. This is just one-dimensional problem, by the way, just for simplicity. We're working 1D. And by drawing lines here for the initial and final positions and the initial and final times, we get a rectangle in the space-time plane. The lower left corner is the x0, t0, which we think of as initial position and initial time. And the upper right corner is the x1, t1, which is the final position in time. Now, when we define a path as a function x of t that passes through these initial positions, these given endpoints and end times, so it satisfies the condition that x evaluated at t0 is equal to x0, and x evaluated at t1 is equal to x1. If you sketch it on the diagram here, a path is a curve that goes through here like this. I'll call this x of t. It's a curve that passes from the initial to the final positions and times, which are just fixed. These are just fixed parameters of the problem, these four numbers, x0, t0, x1, and t1. Now, so this is what we mean by a path here. Even though this is classical mechanics, there's no requirement that this path satisfy the classical equations of motion, Newton's laws, F equals ma. It can be any path, although we will require it to be continuous, because you're usually continuous and actually smooth, because that's what you usually want in classical mechanics. All right. So this includes lots of crazy paths that have nothing whatsoever to do with the classical motion. They may go off in the wrong direction. They may linger at some point for a while. I derived, in the first place, a discretized version of the path integral, which I'll circle here, put in a box. It's represented as the limit as n goes to infinity. The path integral is an expression for the propagator, which we call k, which is otherwise the matrix elements in position space x of the unitary time evolution operator. You think of x0 as an initial position and x0 as a final position. This is over a time t that ranges from 0 to a final time just called t here. In other words, t is the elapsed time. The epsilon that appears in here can be thought of as a delta t. It's the fixed time interval divided by capital N, a parameter which is allowed to go to infinity, so that epsilon is a kind of a delta t which goes to 0. It's splitting up the time interval, finite time interval, into a large number of very small increments. And for each one of those, there's an insertion of a resolution of the identity, which is where these integrals come from. Last time we also explained how this integral can be interpreted, the path integral, this discretized version, can be interpreted as an integral over paths in configuration space. In the discretized version, these are discretized paths. But the exponent that appears here is apparently, or formally at least, it is a Riemann sum, an approximation to a Riemann integral. And we can write the integral in more compact form as a of x of tau. Tau here is a variable that just goes, it's a time-length variable that just goes between 0 and t. I'm using the symbol t here to stand for a fixed final time. So tau is a variable time that runs between the initial and final times like this. And the integral that appears here, formally at least, in the limit that n goes to infinity, it takes the form of a Riemann integral, which is the integral of the, denoted here as a of x of tau, but it is in fact the means, and show you how this works out. So let's take a path x of t, which need not be a physical path, and let's consider another path which is nearby. So I'll sketch it here. It's supposed to go through the same endpoints at n times as the original path. So let's call it x of t plus delta x of t, for a nearby path. It's important to understand this notation delta x of t. Delta x of t is merely the difference between two paths that satisfy the endpoints of n-time conditions. But delta is not an operator. Delta of x is a function of time. However, the delta is a reminder that it's supposed to be small, because we're talking about two paths that are nearby one another. So this function delta x of t has to satisfy the condition that delta x of t0 and delta x of t1 must be equal to 0, because otherwise the modified path wouldn't pass through the given endpoints and end times. But just a condition we impose on this. Now, let's take this action and let's evaluate it instead of on the original path, let's evaluate it in the modified path. Like this. So what do we get? Well, the action function along the original path, let me write this out. This is the same thing as integral from t0 to t1. The mass over 2 times x dot of t quantity squared minus the potential evaluated at x of t. And that whole thing integrated over time. This is just what we mean by integrating the whole dt to Lagrangian. We just take our path x of t, we differentiate it, get an x dot, plug it into this formula, we integrate it as a function of time, we do the integral, the number comes out, and that's what we call the action along the path. And remember that this does not have to be a physical path. All right, now let's evaluate the action of the modified path. This is the integral from t0 to a long time, and then zing over to the final condition to get there at the right amount of time. There's all kinds of crazy paths that are in there. Now, for each one of these paths, we define a functional. We define a number. It's called the action functional. And it's defined as an integral from t0 to t1 of the Lagrangian function evaluated on the path, x of t, x dot of t, dt. It's an integral over time of the path, of the Lagrangian taken along the path. The Lagrangian is an ordinary function of x and x dot. It may also depend on time, but for simplicity, let's just say x and x dot here like this. And in the problems we're interested in, this is m over 2x dot squared minus v of x. We're just talking about simple one-dimensional kinetic energy, potential energy problems. It's kinetic minus potential energy. So that's the Lagrangian that we'll use. Anyway, this A is called the action functional. And it's defined on all paths, whether or not they're physical from a classical standpoint. Action functional. All right. Now, there is, however, something that characterizes the physical paths. As to say, if x of t is physical, this is called, let me write this out. Right? This is called Hamilton's principle. So I'll write that out. Hamilton's principle, which was enunciated at least 100 years before quantum mechanics, says that x of t is physical. That means it satisfies Newton's laws, if and only if the functional derivative of the action with respect to the path x of t is equal to 0. Now, you may not have seen functional derivatives before, but I'm assuming you've seen at least a sketchy aspect of Hamilton's principle in your classical mechanics course. So let me elaborate on what this